we want to evaluate whether this series converges absolutely, conditionally, or not at all. So the first thing you want to check is if the absolute value of the sequence converges. Because if it does, then it converges conditionally. It converges absolutely, nothing else you have to check. Okay. If the absolute value of the sequence, if you try to evaluate that sequence from n equals 1 to infinity, if that doesn't converge, if that diverges, then you need to check to see whether it converges conditionally. And I have on the screen what we need to do, the alternating series test. If the absolute value diverges, then we need to proceed to the alternating series test, because maybe this term here is causing us to alternate, causing the thing to converge conditionally. So first things first, let's evaluate the absolute value. That just basically means this term is gone. So we want to know whether this series converges, and to do that, you could compare it to a p-series. This is 1 over the square. This is similar to the 1 over n to the 1/2 power. And usually in this course, there's a few other examples, but a lot of the series we're comparing are to p-series. This is a p-series that diverges, right? So we want to make some sort of comparison to this series, and depending on which strategies you use, that we could use the comparison test and try to think of something, or the limit comparison test. The limit comparison test is where we would take the first sequence and divide it by the second sequence. I'm just going to flip and multiply the fraction right off the bat, because it's a sub n divided by b sub n. And we're evaluating that limit as n goes to infinity for the limit comparison test. So if you try to evaluate that limit, this is this square root of n over the square root of n plus 4. And so the limit as n goes to infinity, the plus 4 isn't going to really matter, right? Because as n goes to infinity, it's really the n term that's leading the charge here. This is going to converge to the number 1. And so using the limit comparison test, if the limit of the ratio of the two sequences, a sub n divided by b sub n, we flipped and multiplied here. If that limit equals a number, then if b sub n diverges, so does a sub n. So since this diverges by the limit comparison test, this also diverges. So the absolute value, it diverges. So it does not converge absolutely. Okay. So we need to just go back to the drawing board. Now we've taken out the absolute value part. We do not have something that converges absolutely, but maybe it converges conditionally. Maybe we can spot convergence by using the alternating series test. And the alternating series test says, look at the next term in your sequence. So I'm looking at -1, this is n plus 2, and it's times 1 over the square root of n plus 5. Right, because it's n plus 1 plus 4. So this is the next term. If the next term is less than the current term, less than or equal to, so this would be -1 times n plus 1, but that part doesn't really matter as much, okay? If the next term is less than, that term actually does not, there we go. That part does not matter, because b sub n is supposed to be everything except the alternating part. So if the next term is less than or equal to the current term, then we can say it converges using the alternating series test. Is this less than this? It is, by just a tiny amount, because the denominator is just a little bit bigger in the n plus 1 term than it is in the n term. So we can say it converges conditionally by the alternating series test. Oh, sorry, and I just dropped this last part, but it's just the limit as n goes to infinity has to equal 0, right? And it does. Limit as n goes to infinity here goes to 0, because the denominator gets infinitely large, and then you could check it for the n term too. But this converges conditionally, because it does not, the absolute value does not converge, it diverges. But by the alternating series test, this part does converge, so it converges conditionally.